Good morning students. Today we are going to take numerical based on feed water heater, that is open feed water heater, closed feed water heater. In this topic we discuss some methods how to solve this numerical. The first of all, whenever you solve this numerical, first of all you find out you have to assume some assumptions. Some assumptions are to be considered. The steady operating condition exists. The first one. Then you have to consider kinetic energy and potential energy are negligible. And then after that you have to consider the fraction of steam extracted is determined from steady flow energy equation balance. That means in this topic you have to consider steady flow energy equation applied to this feed water heater. That is Q equal to W equal to delta K equal to delta P equal to 0. Then in this system you have to consider in energy in minus energy out equal to delta E system equal to 0. Then we can write summation inlet equal to summation outlet. That means in open water heater and closed water heater you have to consider steady flow energy equations. The first of all we are going to first numerical based on the open feed water heater. The numerical number one, consider steam power plant operating on the idle regenerative ranking cycle with one open feed water heater. Steam enters the turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. Some steam leaves the turbine at a pressure of 1.2 megapascal and enters the open feed water heater. Determine the fraction of steam extracted from the turbine and the thermal efficiency of the cycle. The first of all, you have to identify the numerical. The numerical belong to which cycle? The reheating cycle, reheat cycle, regenerative cycle, open heat power, open feed water heater, or closed feed water heater. That means first what you identify. The first of all, this numerical belongs to the open feed water heater. Then what is given in this case? This is not the part of the regenerative ranking cycle. The first of all, you have to read this numerical once again, and you have to find out what is the input given in the numerical and what are the output to be determined. The first of all, you have to draw the diagram open feed water heater. What is happening in this case? First of all, the open feed water heater, again the cycle is consist of the pump 1, pump 2, open feed water heater, and then boiler, then turbine, then condenser. In this numerical, from this diagram, first of all you have to draw the TS diagram, and you have to locate the point 1, 2, 3, 4, 5, 6, 7 to 1. Then in this case what happened? In this case, given the first of all, given the steam enter the turbine, that is the steam entry takes place in the turbine section having the pressure 15 megapascal and 600 degrees Celsius. Then in turbine section what happens? The pressure having a 15 megapascal having a temperature 600 degrees Celsius, that means the steam is superheated because the temperature is more than 100 degrees Celsius. Then it's condensed in the condenser at the pressure of this one. Again the steam is expanded the turbine section, the work output done in this section, and then the steam having after leaving the steam from the turbine and enter into the condenser section. And that time the pressure of the that steam with steam equal to 10 kilopascal, 10 kilopascal in this case. And then the some steam leaves the turbine at a pressure of 1.2 megapascal and enters into the open feed water heater. At the same time, the steam is entered into remaining steam is entered into the condenser section. At the same time, the steam is entered into the open feed water heater, having a pressure 1.2 megapascal in the open feed heater. And when the steam is entered into the condenser section, that time the pressure is 10 kilopascal. In this case, this is the input data is given. Determine the fraction of steam extracted from the turbine. The new in this numerical is asking the numerical is asking how to find out how much amount of dryness of fraction of steam is enter into this open feed water heater, and second is the thermal efficiency of the cycle. That means you have to find out what is the thermal efficiency of cycle. That means again you go to the diagram. In this section what happens? In boiler section the heat is added, and then heat is added, the temperature of water increases, and then the steam is generated in this boiler, and the steam is entered to turbine section. Turbine section, the work done in the turbine section, and then steam enter into the condenser section, the steam enter the feed water system. And then after this steam is condensed and having a steam is converted to the water and then into the enter into the open feed water through via pump 1, and then again the steam is entered to the open feed water heater. The steam is converted into the water, and then you have to again enter enter into the boiler through via pump 2. And the different types of pressure is having in the different sections, temperature is given, and then you have to go to the solution section. What is given? First of all, I already discussed about this one. Whenever you solve the numerical belongs to the open fluid heater or closed fluid heater, that time you have to assume the some assumption. Again, this is numerical given the steady operating conditions. Delta K and delta P are negligible. That is the changes in the kinetic energy and potential is negligible, and either regenerative ranking cycle you have to consider in this case. So first of all, you have to find out the fraction of steam extracted from the turbine. So how to find out? Because you have to find out this formula S3 minus from, listen to the diagram, and this is the third section. This is the point. This is the point 2. This is point 6. This is point 3. You have to, this is the area in which you have to find the fraction of steam. That is the turbine outlet and the condenser outlet and the feed water inlet, and this is the turbine inlet and condenser inlet and open water outlet. This is the area in which you have to find y equal to h3 minus h2 and s6 minus s2. This is from this diagram you have to find out this equation, and then go to the state 1. Then go to the state 1. P1 equal to 10 kilopascal. Again the 10 kilopascal means that is nothing but the pressure entering in the steam is entered the condenser. That time the kilopascal is the condenser pressure, and condenser pressure, and from condenser pressure saturated liquid you have to determine the value of enthalpy H1, entropy having specific volume. You have to find this from steam table data. You have to use the steam table data. You have to find these values, and then point state 2. This state 2 point you have to 1.2 kilo megapascal. That means the pressure 1.2 megapascal. That is the steam leaving the turbine and the steam entering into the open fluid water. That time the pressure is 1.2 megapascal. That is the open fluid water heater section. The state 2 P2 is 1.2 megapascal. Again the entropy is same. S1 equals to S2. Again go to this point. S1 equal to S2 because this is the TS diagram. From TS diagram S1 equal to S2, and then find out the pump work. In pump working means that is the you have to p specific column in bracket p2 minus p1. That is the again pump in, that the pump in this, listen, this case this is p2 minus p1, and this is the section you have to concentrate that section. This is the condenser inlet and pump outlet of the pump 1. This is the area, that is S2 minus P2 minus P1. You have to put the values and you will get the pump for 1.2 kilojoule per kg. Okay, then we are getting the pump work W pump 1. You have to find out the S2 by S2, then addition S2 pump 2. Pump to S2 equal to H1 plus W pump. This is the formula is very important for you all the students. You remember this formula because S2 equal to H2 plus pump work, and you have to put the values enthalpy of at point 1 plus pump work 1.2, 191.8 plus 1.2 you will get the 193.01 kilojoule per kg. This is the enthalpy at point 2. Then point state 3. At state 3 again go to state 3. This is the point state 3. Again this is the feed water. The water is leaving the feed water and entering the pump 2. This is the section, and again go to this section page 3. Again the 1.2 megapascal such a liquid. Again go to the steam table and you have to find out the specific volume, and yes the enthalpy at point 798.33 kilojoule, and this is the point 3. Then point 4 you go to point 4. What happens? P4 equal to 15 megapascal, and yes for equal to yes. That this means that is the isentropic process. That is the entropy is same 0.334. Again go to the this diagram 3 to 4. Listen, 4 to 3 perpendicular to the yes. Therefore S4 equal to S3. Okay, and then find out this equation from at point 4 15 megapascal. 15 megapascal, that means the again the feed water enter into the turbine. That time the pressure of that water having 15 megapascal. That means go to the again steam table At the steam table, P5 to 15 megapascal, TS is the 600 degrees Celsius. You go to the steam table, you have to find out the value of enthalpy and entropy. The enthalpy is H5 equal to 3583.1 kJ per kg and H5 equal to 6.6796 kJ per kg. This is the values getting from this steam table. Then go to point 6, state 6, that the PV, the boiler pressure 1.2 megapascal and S6 equal to S5. Again S6 S5, again just go to the steam table TS diagram. S5 equal to S6, there is a perpendicular to that means the entropy is same, S6 equal to S5. Okay. Then after getting this, the value of this one, after getting this 5 1, the S6 1.2, again you go to steam table, you have to find out the values HB and TB. You are getting the HB and the enthalpy at point B, that is the 2860.2 kJ per kg, and you get the temperature 218.4 degrees Celsius. And then point 7, you go to point 7, there is point 7, again you point 7, listen, the point 7 is there, point 6 is there, point 7 is there, that is the lies between the turbine and condenser. The point 7 is again 6, 5 in between the 5 and 1, 7 point, and go to this one, P7. P7 equal to 10 kilopascal. Again the entropy is same. S5 equal to S5. S7 S5. The S5. Listen. This is the S5 S7 perpendicular line. That means the entropy is same. Therefore S5 equal to S7 from the TS diagram. And go to find out the values by x7 equal to s7 minus sf by sfg. This is a formula for which to find out the value of x7, the Dynamis fraction at point 7, that the 6.6796 minus 0.6492 divided by 7.4946, Dynamis equal to 0.804. This is Dynamis fraction at point 7. And from 7 you have to get, if you are getting the Dynamis fraction, you will automatically find out the enthalpy at point 2 with the standard formula H equal to HF plus X HFG. You have to find out S7 equal to SF X7 into HFG. Put the values 191.81 plus 0.80 plus 1 in bracket 2392.1. Put the values, will get S6 here, that is the enthalpy at point 7 will get 2115.3 kilojoule per kg. And then this numerical belongs to the open feed water heater. Therefore you have to assume the energy analysis, that is you have to use the steady flow energy equation. Then write down the energy analysis of the feed water heater. EM minus E out, E in minus E out equal to delta E system. Then put the values, and this equation can be getting from the equation this for you. Again go to diagram. Again diagram, this is the in this diagram, enter into this one. Again the 1.2, the steam is enter into the feed open feed water, and then the steam is enter from the condenser to the feed water. Then leaving the feed water, you go to the section. This is the pump section, and you have to consider the point. The YHB equal to 1 minus Y S2 equal to 1 S3. Then Y equal to MB upon MS. Y equal to S3 minus S2 minus SB minus S2. Put the values 798.33 minus 193.01 divided by 2860.2 minus 193.01 equal to 0.227. Then you are getting the Dynamis fraction of the Y point. And therefore you have to determine the what is the heat addition takes place and heat rejection takes place, what are the output is given. The heat input is given by H5 minus H4. You go to the against the diagram, H5 minus H4. H5, listen the point, H5 minus H4. This is the area, the boiler area in between the boiler turbine and feed pump to valve. This is the area in the heat addition takes place, and this is the area condenses. This is the area the heat rejection takes place, and this is the area turbine the work output done, and this is the area you have to supply the water. And then you have to write down the equations. Q in that is H5 minus H4, 358, 358, 3.1 minus 814.03 equal to 2769.1 kg per kg. This is the value to be given, that the heat addition takes place added in the 2769.1 kg per kg. Q out, that means the 1 minus Y, S7 minus S1. You have to put the value, you are getting value 1486.9 kg per kg. You have the Q out. And then find out the efficiency of the cycle, that means again the work input upon the heat supplied, the 1 minus Q in upon Q out equal to 1 minus 148.92969.1 equal to 0.469. Then you multiply the 100, you will get 46.3%. In this numerical you have to study The open feed water, this numeric belong to that one. In this case, your open feed water heater, in this case you have to find out the dynamic fraction of that one, and you have to find out the efficiency. The after getting in this the same numerical, that is the numerical belong to the regenerative ranking cycle. In addition to that, only the open feed water is added. Therefore this is the one more device is added in this diagram, and that therefore the point is the 3 to 6 is this is the area in which regeneration takes place. And open pit water heater, that is the pressure at different section, at different sections: turbine section, condenser section, open pit water section. And this is the end of the first numerical. Let us will take the another numerical based on the closed feed water heater. Like the second numerical, a steam power plant operates on an ideal regenerative ranking cycle. Steam enters the turbine at 6 megapascal, 450 degrees Celsius, and is condensed in the condenser at 20 kilopascal. Steam is extracted from the turbine at zero point 0.4 megapascal to heat the feed water in a closed feed water heater. Water leaves the heater at the condensation temperature of the extracted steam, and that the extracted steam leaves the heater as a saturated liquid and is pumped to the line carrying the feed water. Determine first one, net work output per kilogram of steam flowing through the boiler. A second one, thermal efficiency of cycle. Again, first of all, read the once again, and you have to identify the numerical, which type of numerical is given there in the examination or any in your syllabus. The first of all, you have to identify again the numerical belong to ranking cycle, the regenerative ranking cycle. And regenerative ranking cycle in which the closed feed water heater is added. Therefore, this numerical belong to regenerative ranking cycle having a closed feed water heater. The first of all, you have to draw the diagram. The first of all, in this case, you draw a diagram again the boiler, turbine, and condenser and pump. And in this case, you have to add this is the turbine section, and this turbine section to pump one. You have to add the feed water open or closed feed water heater, closed feed water heater, and again the mixing chamber is added in this case. And this is the different sections. Okay. Then first of all, draw the TS diagram. From TS diagram, you have to locate the points in which locate the point in which the from TS diagram we have to locate the again the point down saturation curve. You have to locate the point 1, 2, 8, 4, and 3 to 5, 5 to 6, 6 to 7, 7 to 1. And there are different sections. This is the boiler section, this is the condenser section, and this is the regenerative section, the feed water heater section. Then first of all, you have to read once again the numerical. What is the input is given, and you have to find what is the output to be find out. First of all, steam enters the turbine at 6 megapascals per 50 degrees Celsius. Again, that means having the steam pressure 6 megapascal. Okay, it's okay. In this case, that is this is the section. The at the point 5, you have to this is the steam enter into turbine that time having a pressure 6 megapascal and 450 degrees Celsius temperature. That is the steam is superheated because the temperature is more than 100 degrees Celsius. Then it condenses in the condenser 20 mega kilopascal, and that time the steam leaving the turbine and steam is entering into the condenser section. That time the pressure is 20 kilopascal at condenser section. After that, the steam is extracted from the turbine with zero point 0.4 megapascal to heat to the feed water in the closed feed water heater. That the same time the turbine leaving the steam leaving the turbine and entering into this one closed feed water heater. That time the pressure developed in this area is the zero point 0.4 megapascal. After that, when leaves the heater at the condenser temperature of the extracted steam leaves the heater as saturated liquid and pumped to the line carrying the feed water. That means in the numerical, the steam from the turbine enter into the closed feed water heater and enter into the condenser. And then in this numerical discuss about that is the steam enter into the open closed feed water heater. That time again enter into the again into the boiler section through pump and at the same time it's converted into the steam into the water, liquid water. Then in this numerical you have to determine the network output. Network output first of all, and second, efficiency of cycle. That is efficiency of cycle you determine. Then again you have to find out the there are four five components are there. The boiler, turbine, condenser, pump, and open close water heater. Then you have to find out the each section. You have to find out the enthalpy of that one, entropy of that one, and then you have to determine work input, work output, heat rejected, heat added, and then from the pressure, so pressure and temperature. For to solve this numerical, you should know the how to use the steam table. The from steam table you are getting the values. Then start the numerical. First of all, again, I last time I already discussed. You have to assume some assumptions. The steady operating conditions exist. A kinetic energy of is negligible, and then from steam table you have to find the enthalpy H1, and this is the specific volume for getting the values. This one H1 equal to 51.42 is the enthalpy at point 1, and specific volume 0.001017 meter cube per kg. That is the point 1. You have to go to point 1. That point 1 you have to find out the values from the steam table you are getting here. Then you have to find out the pump work, because this numerical, in this numerical the main thing is that what is the steam is converted, when the water is converted to the steam and steam converted into the water, the conversion. That is the, and in each and every section what is the conversion takes place, and what are the processes has been done, and what are the enthalpy of that stream, enthalpy of the enthalpy of the stream, the entropy of the stream, and you have to determine how much amount of heat is added, how much amount of heat rejected, how much amount of work done obtained, and what is the efficiency of the cycle. This is a similar case in this case, only the different devices are put in this case open feed closed feed water heater, therefore the efficiency is different. Therefore, you have to at each and every point you have to find out the enthalpy and entropy, and then you have to decide what is the equation may be. Then you are getting the pump work with 6.08 kJ per kg. Then you have found S2 equal to H1 plus WP1. This is our last time we have already discussed. You have remember this formula S2 equal to H1 plus WP1. You are getting S2 values to 57.50 kJ per kg. Okay, and then go to the another section. Then to determine the S2 point, that is enthalpy at point 2, H1 equal to WP1. Again the same form repeated. You have to put the values, enthalpy values you are getting to S2 value enthalpy at point 2 to 57.50 kg per kg. Then at point 3, the P3 is the 0.4 megapascal. So what happens again? This is the point you go to point 3. You go to point 3, and that point 3 you have to find out the value of enthalpy and entropy. From the stream table, you have to get in the values. Enthalpy S3 equal given, and specific volume is given. Then again, the find out pump per second. Pump per second, again the specific volume into the pressure difference P9 minus P3. Then you have to put the values. We'll get the 6.07 kJ per kg. Pump work 2. Go to the pump work 2. This is the pump work 2. This is the pump work 1. This is the pump work 2. This is 9 section, 3 section. Therefore, this is the area. From this area, you have to define the pump work, and this is the pump work you are getting in this case. Uh, and then go find out the H9. That is the enthalpy at point 9. S3 plus W pump work 2. Again, go to this diagram. Listen, and this is the H9, and this is the pump 2. This is the 3 point. Pump 2 lies between the 9 and 3 point. Therefore, you have to consider this section, and you have to find out that. And in this case, H9 equal to S3 plus pump for 2. You will get 0.73 kg per kg. This is the H9 enthalpy at point 9. Then find H8 equal to S3 plus specific volume P8 minus P3. How to find out? Equal to H9 equal to 610.73 kg per kg. Same values, because you have to go to this diagram, and from diagram is the same 8 point and 9 point, same value to be obtained. Therefore H9 equal to H8. Then you have to consider also H4, H9, H8 0.23 kg per kg, since the two fluid streams which are being mixed have the same enthalpy. That means whenever the the steam is entered this one, the steam is converted to that one, and this from this point to that one. This enthalpy of this area in this mixing chamber, the H9, H8, the enthalpy are same. Again, the 4 is point out, 4 is out, and 8 and 9 is enter into the mixing chamber. This is the region in which you have to find. Therefore, this numerical given that the H4 equal to H9 H8 6.10.73 kg. Since the two fluid stream which are being mixed have the same enthalpy, Then go to the another section P5. Again go to the P5, that is the again section P5, the point P5. P5 is the form TS diagram. You go to P5 point. 5 point you have to locate the values. TS diagram 4 degrees Celsius. Again, this is the temperature more than 100 degrees Celsius. That means the superheated steam, and that superheated steam have to consider from the steam plug. You have to find out the value H5 equal to this one, H5 is equal to this one. You are getting this enthalpy and entropy value. Then PV, the boiler pressure 0.4 megapascal, and S6 is H5. Again go to this diagram. S6 and H5 is same, there the entropy is same. Therefore S5 equal to S6. Again S5 equal to S7, then the entropy is same. Then go to this one, and from that you have to find out the dryness fraction of that one. Put this formula and you will get dryness fraction is equal to 0.9661. Then you have to find S6 HF plus HHFG. The same formula is repeated. You put the values, you will get the value 2665.7 kg. This is the S6. You are getting the enthalpy at 0.6 and you are getting the dryness fraction at 0.6. That is, again go to this diagram. This 6 diagram, this is the 0.4. This is the area. This is the area turbine to close feed water. In this case, what happened? This is the enthalpy is given and dryness fraction is given. After that, you go to the P7 section. 7 section is the 20 kilopascal. And again S5 is 7 because again go to this one. S7 to S5. 5 to 7 is the line perpendicular to the entropy that is the same. And then you have to find the dryness fraction and enthalpy. You have to put the values again, the same formula S6 7 by S7 SFG. The formula is same repeated in this case 6 7 and 7 is. You have to put the values, you are getting 0.8325. And then find out S7, that is the enthalpy at 0.7, and HF plus SFG, that is the 251.42 plus 0.8325 into 2357.5, you will get a 2214 kilojoules per kg. That means you are getting the X7 at 7 point. Listen, from this diagram you are getting the steam is remaining steam enter into the closed feed water heater, and the steam is enter into the waste to enter into the condenser, and then you are getting the S7, and you get the S6, and from the data you have to find the X7, the dryness fraction point entry of the condenser, and S6 the dryness fraction of the steam entry into the closed feed water heater. This is the value to be asked in the numerical. So we are getting this value. We are getting this value. S6 is the 0.9961 is the closed feed water heater, and the X7 is for 0.89 the dryness fraction point entry into the condenser. And then you go to the fraction of steam extracted is determined from the steady flow energy balance equation applied to the feed water heater. Whenever the numerical belongs to the open feed water heater or closed feed water heater, that time you have to consider steady flow energy equation. And therefore noting that Q equal to W equal to delta I delta B equal 0. Because there is a consideration in these assumptions. Then energy in minus kg out, delta E, that is the system. You have to equating that equation, this is the inlet area, this is the exit area, and you have to find out the inlet area H8 minus S2 and S6 minus S3. Listen, go to again 8 minus 2 H8. This is the point again. You have to go to this one. This is the point 8 and this point. Listen, this is the area 8 to 2 point. Listen, the pump work area region, and this is the 8 point enter this one 8 to 2 point in this case. And then again 6 minus 3, yes, 6 minus 3, again 6 minus 3 is the 6 point and 3 point, and this is the area, this is the area, this is the area, because this is the center point is the closed water heater, is the closed water heater. 6 to 3 and 2 to 8. And from this diagram, we have to find out put the equation m dot 2 equal to h8 minus h2 and m dot equal to h3 minus h3, and from put the values the 1 minus y h1, this one y h6 minus h3. The y the fraction of steam extracted from the turbine, therefore m6 by m5, solving this, this is the fraction of steam. Okay, then you have to find y. How to find out the y? The y equal to h8 minus h2 upon h6 minus h3 plus h8 minus h2. Again the same thing, you have to put the value, will get the 0.1463, you are getting the y Dryas fraction, that is the fraction of steam extracted from turbine, how much amount of steam is extracted and enter into the condenser section and open and close it, close heat water heater, feed water heater. Then you have to find out q in, how much amount of heat is added in the cycle, and q out is the how much amount of heat is rejected. And then for the total work output, the q in equal to h5 minus h4. h5, listen, this is the area h5, this is the area boiler 5 to 4, this is the area heat addition takes place, and this is the area in which the heat rejection takes place, condenser. Heat rejection takes place and heat addition takes place in this. You have to write this equation for the diagram. You write this equation, and the q in equal to h5 minus h4, put the values, will get in 2692.2 kg per kg, and then q out 1 minus y h7 minus h1, you are getting 1675.4 kg per kg. For finding out these two values q in and q out, you will find out the w net, q in minus q out, and you are getting this one 1016.8 kg per kg. This is the w net. Work done. Then find out the thermal efficiency of cycle, that is again 1 minus q out upon q in, put the formula, and then you have to put the values, you are getting 37.8%, that is 0.378, you have to multiply by 100, you will get 37.8. That means from this diagram you have to conclude that this is the, you have to find in this numerical how much amount of steam is extracted from the turbine and enter into the closed feed water heater and enter into the condenser section. You have the first one, then you have to find the efficiency of the cycle. And today we are discuss about the two numericals which belong to the open feed water heater and closed feed water heater. And this is the end of the today's session.